So you guys, law of conservation of energy. That's what we're going to talk about. And here's what IB expects you to know in terms of the law of conservation of energy. You should be able to state the principle of conservation of energy. You probably already can, right? You should be able to list different forms of energy and describe examples of the transformation of energy from one form to another, distinguish between elastic and inelastic collisions, and solve problems involving momentum, work, energy, power. That's what we're going to do today. It does. All right, here we go. We're doing it again. And, oh goodness, boom, boom. There we go. So here we go, law of conservation of energy. Pretty straightforward. Energy cannot be created or destroyed. It can only change forms. So when you're dealing with problems with the collisions and explosions, think momentum first, because momentum is always conserved in an isolated system. Energy, it's conserved, but you might have different forms. So if you try to solve it with like kinetic energy, well, the kinetic energy might not have stayed the same. So that gets kind of tricky. Einstein later modified this law when he came up with this equation E equals mc squared and the relationship between mass and energy, and he discovered that mass can actually be turned into energy, and energy can actually be turned into mass. So you can have a system where you have a whole bunch of energy, and some of that energy will disappear if it becomes mass. So now we have, some people call it the law of conservation of mass and energy, because mass is just, some people think of mass as like a type of energy, a type of potential energy in some ways, okay? That's the way nuclear bombs are made. And when we get into nuclear physics next year, we'll talk more about that. All right? Okay, so let's talk about the gentleman lifting a large boulder while standing on a small footstool, which is strange. Why is he standing on a footstool? I don't know. But when he lifts the rock up, does he do work? Yes. And what's the equation for work again? Great. Force times distance, or S for displacement. Great. In this case, to lift it at a nice constant velocity, how much force does he have to exert? How much does it what? Weigh. That's what you'd like to know, right? You'd have to exert the amount of force as equal to its weight. Yeah? And you know that weight is mass times 9.8, gravitational field strength. Okay? So the force that he does is that, and the height that he lifts it is h, mgh. That looks familiar. So when you do work on an object, you give it energy. When he lifts the boulder, what kind of energy does he give it? How much potential energy does he give it? Which is mgh, right? So suddenly it has this much energy, mgh. You with me? Okay, he did that much work, he gave it that much energy, and it's got that much potential energy now. When he drops it, it starts to fall. Does it have the same potential energy anymore? The potential energy is going away. But it's changing. It's changing into kinetic energy because energy cannot be created or destroyed. It can only change forms. So as it falls, so as that rock is falling, that potential energy is going to start becoming kinetic energy. Right? And halfway down, it's got half the kinetic energy and half the potential energy. Right before it hits the ground, not once it hits the ground. You guys always think, well, what's the speed when it hits the ground? Well, 0. But what we mean is what's the speed right before it hits the ground. You can figure that out now because all of this potential energy will have become kinetic energy at that point. Well, you could do a little bit of math. Let's see what we could do. I could take my potential energy, and I could say, hey, it's going to become kinetic energy. Does that make sense? And now look, if I want to solve for how fast is it going to be moving right before it hits the ground, mass cancels out. 2gh square root is equal to final velocity. So there's an easy way to find the velocity of an object if I know its potential energy is turning into its kinetic energy. Okay? This equation looks very similar to another equation you've seen. Look at this one. Final velocity squared equals initial velocity squared plus 2as. If the initial velocity is 0,
but it's the same thing.
it's the same thing. Then the final velocity is the square root of 2as. That's exactly the same thing. Accelerate. G is the acceleration of gravity. H is the displacement. Okay? So they're all kind of related. All right? So this is an example of doing work to give something potential energy, gravitational potential energy, and then having that turn into kinetic energy. But you could also do something like this. I could do work in pushing this spring and compressing that spring, and that would give me elastic potential energy. There'd be energy stored in that spring, right? And so this is like some of the homework problems I think you guys are talking about. And one of the equations we glossed over last time is that the potential energy stored in a spring is equal to 1/2 K, which is a constant called the spring constant, which tells you basically how stiff or how loose the spring is, times how much x times 1/2 kx squared. X is how far you've either compressed the spring or how far you've stretched it. So if I know the spring constant, and I know how much I've compressed the spring, I can figure out how much potential energy is in there. So I've done this much work, I've given the spring that much kinetic energy, and then I release the spring and the ball. Right when the ball leaves the spring, I could say, well, look, all of that is now going to be kinetic energy, 1/2 mv squared. And I could solve for how fast the ball's moving. And then I could say, ooh, all that kinetic energy is going to become potential energy, and I could solve for how high it goes. Okay? I could set these things equal to one another using the law of conservation of energy. Let's look at roller coasters. You notice that roller coasters, I mean, there's a lot of cool things about roller coasters, but usually the first hill is the biggest. It's very hard to have a roller coaster where a subsequent hill is larger than the one before it because of conservation of energy. They work on gravitational energy. So if you're going to solve for how fast it's going at the bottom of the hill, you want to take the potential energy at the top, and it's going to become kinetic energy. Right? So mgh can be equal to kinetic energy. Notice that you don't need to know the mass of the car. You solve for V. What did you guys get for V? 22 meters per second. Great. Now look at what's kind of nice about conservation of energy, guys. You just found out how fast it's going at the bottom of the hill. Now, if it has multiple hills, and notice that they have to get smaller every time or else we're in trouble. Let's say this hill has a height of, I don't know, 5 meters off the bottom. So 5 meters. Now it would be really easy to figure out how fast it's going at the top of that hill. Because look, you could just say how much potential energy did it lose? And what would H be in this case? It would be 20, right? Because it went down 25 and it came up 5, and then set that equal to potential or kinetic energy, and you're good to go. You can figure out how fast it's moving. You don't even need to know the bottom because it's gaining kinetic.
Don't do it. Tigers alive.
Oh. There. This is for Taggart. Okay, happy face. All right. Let's try this question now. Okay? This is a typical IB type question. You're standing at the edge of a cliff. You throw one ball down with a certain velocity, and you throw another one up with the same velocity but in the other opposite direction. Actually, they have the same speed, different velocities. So you throw one down at a certain speed, you throw one up with the same speed. How will their speeds compare just before they reach the ground? How will their speeds compare? We're neglecting air resistance. Consider it in terms of conservation of energy. So we're all in agreement that it's going to have the same velocity. But let's look at it in a couple different ways. There's a couple different ways to think about this. Okay? No, you're absolutely right. Absolutely right. Okay? So here's the person. And you throw something down with a certain speed, v, and then you throw another thing up with the same speed, negative v. Okay? Let's think about it not in terms of energy. Let's go back to kinematics for a second. If you throw something up with a velocity v, when it comes back to your hand, how fast will it be traveling? Okay? So that's one way. Well, like, okay, this one's going to come up and come down, and when it gets back to here, it's going to be moving down with v, which is exactly like the other one. Therefore, they'll hit at the same speed. Is that all good? But now let's think about it in terms of energy. This one you throw up, you've given a certain amount of kinetic energy, and it's going to go up and become potential energy. And then when it comes back down, that's going to be kinetic energy, and it's going to have exactly the same kinetic energy as the one that you threw down with that much kinetic energy, and therefore when they hit the ground, they'll have the same kinetic energy, same velocity. Okay? So it all kind of works nice and neat. Okay? Okay, the balls will strike the ground with the same speed, but they won't get there obviously at the same time, right? Does that make sense? Like one's going to get there before the other one, but that's not what the question was asking. Now let's think about pole vaulting, which I think is just a really incredibly crazy and awesome sport. But in terms of observing conservation of energy, it's an amazing thing. So let's first of all just think about it. You guys know about pole vaulting? You know what I'm talking about? So the pole vaulter is running down the track. What kind of energy do they have? Kinetic. Then the pole gets into the little pit, and then what happens? But before they launch up, what does it do? It bends. So what did... Excellent. So that kinetic energy of the runner becomes potential energy in the pole, elastic potential energy. And then what happens? It becomes kinetic and lifts the pole vaulter up and converting it to what kind of energy? Potential energy. And then it comes kinetic as they fall back down. Okay, so it's all this energy transformation going on. And you can, if everything was perfect, okay, which is never perfect, but you can imagine that if the pole vaulter doesn't have enough kinetic energy to start, they'll never convert that into enough potential energy to get over the bar. So we can calculate, this is what the question's asking, if you're trying to get over a 4-meter bar, you need that much potential energy at the end. How much kinetic energy do you have to start with to ensure that you can do that? So let's figure that out. How fast must the runner go at a minimum to clear that bar? Okay? So here we're looking at a situation where we're going to take the pole vaulter's kinetic energy, 1/2 mv squared, and it's going to become their potential energy, right? And now we know what we want for H to be, so we can solve for V. And what did you guys get, 8.9? Yeah. 8.9, okay? Let's think about playgrounds and look at slides. Here are 2 slides at the playground, okay? You can go down slide A, you can go down slide B, but the $1 million, $64,000 question is, which slide will get you going faster at the bottom? Let's assume there's no friction. These are awesome frictionless slides. Why would you have the same speed with potential energy? Which one would, so is everybody clear about that? You'd end up with the same speed at the bottom, assuming there's no friction. Which one would get you there faster, though? B would get you there sooner. Okay, because you're going to speed up sooner with B, you're going to get there faster. But you'll end up at the same speed with both of them, regardless of the path taken, because the same amount of potential energy is becoming kinetic energy. Okay, lastly, let's consider in terms of energy transformation. So let's think about one of our favorite activities here in the Greater Aspen Snowmass ski area. Skiing and snowboarding. I don't know about you guys, but I think you should do it if you don't, because it's awesome and it's fun, and that's one of the reasons why we live here. And it's fun to go downhill, right? When you're going down the hill, so when you're going down the hill, when you're going down the mountain, what kind of energy do you have? And that's what's really fun. We like the kinetic energy, right? But where did that energy come from? Okay, so at the top of the hill, you have potential energy, right? And where did that energy come from?
It came from the height of the mountain.
Yeah, but how did you get up there? Most of us take chairlifts. Some people like to hike, but we'll say the lift brought us up, okay? And again, energy is conserved. Where did the chairlift get its energy?
From the motor.
Okay. Most of the lifts here are electrical, and you're right. Yes, it's a motor converting electrical energy into mechanical energy, which is great. So we'll say it's electrical, unless the electricity is out, and then it uses a generator. But most of the time, it's electrical. Where did that electricity get its energy? Okay. From coal. Yeah, here it's from a power plant, right? And here in Colorado, most of our power comes from burning coal. But it could be burning natural gas. It could be burning oil. Those are kind of the 3 big ones. So what do we say? The electricity generally comes from coal here, but there's other sources. Where did that coal get its energy? Okay, so coal and all fossil fuels, we call them fossil fuels because they come from fossils, right? But those were mostly like plants and things that were buried. Where did those plants? Well, let's go back to plants. It's not really dinosaurs. It's mostly plants, but that have been buried for millions of years.
Consider like old plants dinosaurs.
You could if you wanted, I suppose. Where did the plants get their energy?
The sun.
Okay, photosynthesis. Okay.
The fusion, nuclear fusion.
Okay, so the sun gets its energy from fusion. Okay, nuclear fusion. Okay, globbing together some hydrogen and turning it into helium. Yes, yeah. Okay. So fusion's happening in the sun. Where did the energy of the fusion come from?
Comes from the
Big Bang.
Big Bang. Yeah.
It's so condensed and it heats up so much that the atoms move really fast and they bond into each other.
Yeah. But really, nuclear reactions, the nuclear energy is like energy from the Big Bang. It's like a stored energy from the beginning of the universe, which is kind of great.
Where did it come from there?
Oh, now that's a good question. Where did the energy come from that created the Big Bang?
Where's the
You leaving? What's that? Right? We don't really know. So God is as good as answer as any, as far as I'm concerned. And the reason I think it's important for you to consider this is because when you're skiing and snowboarding, you should be thanking God, okay? Because that's where that energy came from, ultimately. And if you don't believe in God, okay, you're welcome to thank the Big Bang, okay? But it's all connected. Energy cannot be destroyed. It's always transforming from one form to another. All right, so there you go. So really this whole discussion about God and the universe was prompted by the idea that energy is never created or destroyed. It only changes forms, okay? So keep that in mind. Law of conservation of energy. Last thing we need to talk about is collisions.
Wait, I want to write that down.
And when things collide, we break them into two types of collision categories, okay? What we call elastic and inelastic. First of all, in a collision, what quantity is always conserved? Momentum. Please remember that. Momentum is your friend when you're talking about collisions and explosions. It makes things easy. Momentum is always conserved no matter what kind of collision we're talking about if it's an isolated system. However, kinetic energy is not. You can have two different ways. This is how I break it down. You can have a collision where kinetic energy is conserved before the collision and after, or where it's not. And think about the train problem we did at the beginning. We had a certain amount of and we had a certain amount of kinetic energy, and some of that kinetic energy disappeared. It turned into other kinds of energy, okay? That's how we differentiate the two kinds of collisions. And we say it's elastic if kinetic energy is conserved, as well as momentum. And we say it's inelastic if kinetic energy is not conserved, but momentum is. Momentum will always be conserved, okay? So those are our two families of collisions, elastic and inelastic. When you're solving problems with collisions and explosions, please remember that momentum is the thing that's always conserved. If you try to solve it by conserving kinetic energy, it might work if it's elastic, but it might not work if it's not elastic. So with that, let's see. This is what we're trying to do. Can you state the principle of conservation of energy?
Yeah.
Go ahead.
Not be created or destroyed, only transfer.
It can only transfer. Great. Can you list different forms of energy? Let's give some different forms of energy. Okay. Kinetic, potential, elastic. What kind of elastic what? Elastic potential. Okay. What other kinds of energy can you think of? Gravitational potential, chemical, which, okay. Nuclear. Great. Those are all really good ones. What does most energy end up as? Heat. And we'll learn next year that heat is just a form of kinetic energy on a molecular level. Okay, that's molecules with kinetic energy. Exactly, exactly. Could you distinguish between elastic and inelastic collisions?
Yes.
Definitely. And could you solve problems? Hopefully, because you have.